So hello everyone. So we'll start uh, the discussion of vector algebra, and this is uh, the first lecture of vector algebra. So what we are going to discuss is vector algebra. Okay. So this is lecture 1. What will be mainly concerned is on the sum of two vectors, and the second one would be multiplication of a vector with a scalar. Okay, so we'll try to say how this is defined, and then we'll try to give some consequences of these two facts, and then we'll try to explain it geometrically. Also, we'll define the equality of two vectors. Okay, so when we say what is a vector, so basically if we have the real line, every point, whatever is it, x0 in R, is a vector. Okay, so what we know is that it's a scalar, but we can say that equivalently that it's an one dimensional vector. So every point in Rn, so in general, if you go to R2, so now we have two axes. So we have some point, let's say this distance is a1 and this distance is a2. Then we have this point a equals to a1 comma a2. So this is a point in R2 if a1 comma a2 are real numbers. Okay, so now this is a vector, and this vector has, this is the picture is not very clear. So this is the vector, and it has a direction, also it has a length. We'll define what is the length. In this case, if this is the origin, this is the vector x0. So in the same way, in Rn, any point a equals to a1 to an, which belongs to Rn, is called a vector. So this is what we define as a vector, where this a1 to an belongs to R. Okay, so now we will try to add two vectors. If we have given 2 points in Rn, we will try to add. So the first one is sum or addition of two vectors. Okay, so basically if we are in R, we can just add x0. Let's say this is one vector and this is another vector. This is just the addition of two scalars. In R2, if we have one vector here, if we have some other vector there, let's say b equals to b1 comma b2, so what we'll try to add them. Okay, this is another vector, so we'll try to add them. So this addition is exactly will be component wise. So you add a1 with b1, a2 with b2. So in general, if we have two vectors, one is a, which is a1 to an, another is b, which is b1 to bn, then capital A plus B is defined as A1 plus B1 an plus bn. So observe that this is also a point in Rn. Okay, this is analytic definition. What does it mean geometrically? Okay, geometric interpretation. When at least we will be able to understand when n is less than or equal to 3. Okay, so let's, for example, we have one vector here and another we have, let's say, like this. So now we draw a parallelogram. So let's say this is the origin. Origin means 0 comma 0. This is some vector b. In 2 dimension we are thinking, and this is some c. So draw two vectors. One is, this is parallel to b, another one which is parallel to c. So we know if we draw a parallelogram with these sides, then the sum of the opposite vertices, which is O plus B, is exactly C plus B. Sorry, if this is some D, O plus D, these are the two opposite. This O and D are opposite, and C and B are opposites. But O is the origin, which is 0 plus 0, which is 0, 0. So this D, this new vertex, is exactly the sum of these two vectors, which you already know, B and C. And more precisely, this B plus C is given by this line, this diagonal of this parallelogram. Okay, so this is the geometrical meaning of this fact. Now, at least in n for n less than or equal to 3, and if for n equals to 3 also, you will get some parallelepiped and the situation will be similar. Now, the second one is the multiplication of a vector with a scalar. So let C belongs to R, 0 or non-zero, and A is some vector which is in Rn. Okay, given by capital A equals to A1 up to An. So then you define C multiplied with A as CA1 up to CAN, which is again in Rn, so which is again a vector. Okay, so basically if you are in R for n equals to 1 case, this is the geometrical fact, geometrical interpretation, and this is for any n bigger than or equal to 1. So if this is the origin, if this is some x naught, so basically C is some scalar, so you are multiplying. So if C is positive, C will be on the positive x-axis, C x naught, let's say C equals to 2, then you will get 2i's of x naught. C equals to half, you will get half of x naught. If you take C negative, you will get the negative x-axis some point. Now see, in a similar way, take any line. This is the vector A. So 2i C is exactly here, half of A is here, and if C is negative, you'll go to this direction. So for example, this will be half minus half of A. So this is geometrically what we mean by multiplication of a vector with a scalar. Now the equality of two vectors, equality of two vectors. So if you have given two vectors, let A and B belongs to Rn, so then we say that A equals to B if AI equals to BI for every I varies from 1 to n, where A equals to A1 to n and B equals to b1 to bn. So a and b are same if all the components are same, and the components are ai and bi. So it exactly says that two vectors are same if all the components are same. If at least one of the components are different, we can say that the vectors are not same. For example, a equals to 1 1 1 2 and b equals to 1 1 1. So first component is same, second component is same, but the third component is different. So a is not equals to b. Okay, so these two vectors are not same, not equal. Okay. So with this definition of equality, along with this multiplication definition and this addition of two vectors, we'll derive some properties in the next lecture. So for this one, we'll stop.